Hello, everyone. Welcome back to The Good Stuff. The Good Stuff being this is the AAS Journal Author Series on the AAS YouTube channel. And I am super happy to have May Pedersen with us today. Hi, May.
Hi.
How you doing today?
I'm doing great, thank you.
Where are you zooming in from?
So I'm zooming in from Belgium right now in Leuven, from my apartment, my office here.
Okay.
Yeah.
I understand you're graduating or you're moving on soon.
Yeah, so I just defended my PhD thesis actually last Monday online.
Dr. Pedersen.
Thank you. Yes, thank you so much. So after 4 years in Belgium, I can now call myself a doctor in astronomy and astrophysics. So that's
awesome.
Very nice.
Where are you headed to next?
Next up, I'm heading to Santa Barbara, actually, in California in September to work at the KITB.
Pedersen. Super. Yes, of course. Very good. Awesome. What do you like to do for research?
For research, I'm very interested in studying pulsating stars, and more specifically, high-mass pulsating stars, basically. So the stars that we call the chemical factories of the universe, basically. So yeah, those are my prime interest, and trying to figure out how well they mix material in their interiors, which has a high impact for their future life after the main sequence as well.
Sure. Very good. And speaking of, so why don't we get right to it for folks, given that research interest. So we are going to walk on, take a deep breath when you say this title, Diverse Variability of O and B Stars Revealed from 2-minute Cadence Light Curves in Sectors 1 and 2 of the TESS mission, selection of an Asteroseismic sample. And May, take it away.
Yes. So just to briefly give a small background for this paper that I have here. So it's a big collaboration work with a working group 5, is it called, that works in O and B stars.
Okay.
That's part of the TESS Asteroseismic Science Consortium. And basically what we really want to do is to use the TESS Space Telescope to get to use the very high quality data from there to study O and B type stars, and more specifically the ones that are pulsating. So that's the asteroseismic sample that we are trying to identify, basically. So this is actually a TESS first light paper. So this was put together a couple of weeks after the first data release of the TESS space mission. And it's kind of also a proof of concept paper to show how much we can potentially learn from the TESS space mission when it comes to O and B type stars and the pulsational properties, basically.
What's the, I mean, I understand they have a variety, but what's the period of these O and B stars? What are the periods of these O and B stars? So
that varies. For the B type stars, the periods are of about 8 hours to 3 days. And the O-type stars, it's of the order of minutes and hours, basically, in that range, depending on the type of variability that they have for the pulsations.
Right. So at 2 minutes, in some cases, you got exquisite resolution.
Yes.
Cases where the periods might be on the order of minutes, a little closer to not being as resolved.
Yes. So this is very, very high cadence compared to the periods. But it's, again, useful for us. And also this was immediately made available by the people behind the mission for us to use. So we jumped on the data to try and see what we can find in these type of O and B type stars. What kind of variability, basically.
Looks like we got... got about 154 O and B stars.
Yes.
Okay.
And the ones that we studied, so those are O and B type stars that were actually observed in 2-minute cadence.
Okay.
So TESS is actually taking full frame images of the sky as it's observing and doing its full sky survey. So effectively it's observing a lot of more O and B type stars, but these are the ones where we have these postage stamps where there's quick pixel extraction with the light curves that we were studying, basically.
Super.
So actually, when you want to do astroseismology, you want to make sure that you have a long time baseline for your light curves. So the longer you observe the star, the higher resolution of your frequencies you get, which is both important to actually resolve and detect the frequencies. And the higher resolution you have, the higher the precision of your frequencies you get as well when you try to do astroseismic modeling.
So what was, was the time baseline that you, how many days or months or years of observation?
Yeah, so for each sector, TESS is observing for about 27 days. But it has a total of 26 sectors. And the first year of the mission, it was observing the southern hemisphere. And the sectors overlap at the ecliptic pole. So there it's observing for about 1 year in total. So all stars falling inside that circle that we call the continuous viewing zone will have about 1 year light curves. So those are the best light curves that we get from the TESS mission. And those are the stars that we're really interested in studying.
Awesome. Very good. Okay. Let's take a look at figure 1. What do we got in figure 1 here?
Yes. So the figure 1 is showing you in black in the background. The small dots are all the stars that were observed by TESS in sectors 1 and 2, plotted in this color magnitude diagram where you have color on the x-axis and you have the magnitude of the star on the y-axis. And on top of this, we plot the 154 OMB type stars for which we did this variability study of. So that's the zoomed in box that you see in this region. That's where you have the OMB type stars. And all the colored symbols, in whichever way they're colored, corresponds to a different kind of variability.
Okay.
So we've been going through the light curves of these stars and their Fourier spectrum to try and classify the variability. So we look both for if they have pulsations, also if they are in eclipsing binary systems, for which we can get even more information than compared to if we have only pulsations. And we're also looking for signatures of a low frequency power excess, so to speak, which we expect to come from internal gravity waves, can generate when you look at the Fourier spectrum. At the low frequency, you will see a bump in the amplitudes there, basically. And that you can generate from internal gravity waves or stellar winds or subsurface convection zones, basically. So we're also looking for these kind of signatures. And this is just taken straight from the light curves. So basically all the black squares are the ones where we see this low frequency power excess, which we call stochastic low frequency signal in this case. And then you have the pulsating stars in blue and various blue colors. And you also look for stars where we see rotational modulations. So if you have spots on the surface of the star, that also gives rise to specific signals in the light curves and the Fourier spectra, basically. So this figure is providing an overview of all the different classifications that we have in this paper and roughly where the stars are at. And all the stars that are marked by a cross behind the symbol are from the Large Magellanic Cloud as well.
Okay. So I see there's one known beta Cephid. So
yes.
Does that mean that all of the other symbols in here, the other stars in here, are discoveries? They weren't known before?
Well, so the majority of the pulsations are new discoveries.
Okay.
For the eclipsing binaries, the ones listed here were known already. But one of them, we also found oscillations, signals in the light curve and Fourier spectrum, and these were not known before. So it was known to be an eclipsing binary, but it wasn't known that it was pulsating, basically. So I think that's also one of the figures a bit later on where you can see the phase folding of the light curve of this binary system, and then see the variability on top from these pulsations that we see.
Very nice. What is the, you got one lone, looks like rotational SPB star out at about a BP minus RP color of about 3. What is that one?
So it's, so in this case, it seems this is actually a very bright star. There are 2 stars in this diagram that are located outside of the box. So this is based on Gaia data, and Gaia doesn't do as well when you go to the very bright stars.
Yes.
So we suspect that's the reason why we end up with stars outside of our box and in places where we wouldn't necessarily expect them to be in this diagram.
Right. Okay. Got it. Very cool. Okay. So there's our color magnitude diagram.
Yes. It's a very nice summary of the results. And
it's
where I'd say that's the,
And then we walk through our classification procedure. And then we talk about the Gaia color magnitude. And what is figure 2 here?
Yes, so that's the eclipsing binary I was talking about before. So this is a phase folded light curve taken by TESS of this star, where you see the overall like sinusoid variability and also the eclipse itself of the star.
Yep.
So that's the binary signal. And on top of that, you see a lot of wiggling. And that's basically from the pulsations that we see in this star. So here we have clear, very strong signal of pulsations taking place in one form or another in this star. So that's so these were not known to be present before we studied the TESS data.
So are both stars pulsating and you're picking both of them up, or is only one of them pulsating and you're picking up?
That's a good question that we don't know yet.
Okay.
It's could be both, could be just one of them. But the signals you'd expect to get more strongly through for the brighter one of the components, I guess. Yeah.
Okay, interesting. Okay, very cool. So we got CMDs, we got eclipsing binaries. Now we have results.
From the classification, yes.
What do we have here?
Yeah, so this is an example light curve on top that we constructed from the TESS data. And on the bottom is the Fourier spectrum of this light curve, basically. So this is an example of a star that shows both gravity modes and pressure modes inside the star. So you have the very long pulsations, good periods, and you also have the very short ones in this star. So this is what we call a hybrid. That's the case when you see both types of pulsation present in this star at once. And I think we found a total of 4 of such hybrid pulsators in this sample of stars that we're looking at. So the good thing about having hybrids is also that if you look at the gravity mode, you have gravity as a restoring force, and they mainly probe the near core properties of the star. Whereas with the pressure modes, you have pressure as a restoring force, and they're more sensitive towards taking place in the envelope of the star. So if you combine both, you should be able to get some pretty good constraints of your star, basically.
Star.
Yeah. Yes. Yeah. So one of the things that we would also be very interesting to do for these stars is to try and constrain their interior rotation rates. So from the gravity mode, you could get an estimate of the near core rotation of the star, and from the pressure mode, you can get it for the envelope as well. So again, to do this, you really need to have the frequencies highly resolved. So this data is not enough. You need to do at least 1 year observations to do this, basically.
So for this particular one or for others, do you find that the surface layers are rotating at the same or different rate than the core?
Also, what's I think is generally found for most stars on the main sequence, for in the range of up to 8 solar masses, what we see is that they're actually mainly rigidly rotating on the main sequence, or we only have measurements of the core rotation rates. So one of our issues is actually that we lack observations for also the higher mass stars. So right now, the best data we have is from the Kepler space mission.
Okay.
But because of where Kepler was pointing, you didn't get to observe the very high mass stars by this telescope. So that's where TESS is really going to help us out, and is helping us out at the moment by allowing us to go to the much more massive stars that end as supernovae explosions in the end.
Mm-hmm. Very nice. So we talked about that, and we talked about pulsating stars.
Yes.
Rotational variability. Here's your stochastic LSFs. Can you say a little bit more about that? Is the star somehow tapping the acoustic power in order to drive some of its evolution?
So the way we interpret this signal is to be due to internal gravity waves.
Okay.
So the stars have convective cores, and this convective core excites what we call internal gravity waves, which travel throughout the envelope of the star. And as they reach the surface, they lead to temperature fluctuations and therefore brightness variations, and the power spectrum that you see for these stars come across as these low frequency power excess, basically. So with power at lower frequencies. So we interpret it to be...
So these are not standing waves, right?
No, these are traveling waves, yeah. So they're, in that sense, they're very different from the gravity modes and pressure modes, where these are coherent pulsations that are, standing modes, and these are traveling waves instead. Yeah. So we know, or what has been shown is that these internal gravity waves are very efficient at transporting angular momentum, as well as also being highly efficient at mixing chemical elements in the envelope of the star. So that's one of the topics of my PhD thesis, that actually been to study this interior mixing of the stars, and also try to see if it could be from these internal gravity waves. So it's not the topic of the paper, but it's one of the future prospects.
Don't leave me hanging. What did you find? What did you find?
Well, what I found was that to be able to explain the pulsations that we see in what we call slowly pulsating B-type stars. So those are B-type stars pulsating in gravity modes.
Yes.
You need to have some structure in the envelope mixing profile. So that can be either from internal gravity waves, or it can be from shear instabilities from rotation, for example. So that's what we know right now. And moving forward, one of the things we need is to include studies of surface abundances to try and investigate maybe which one of the two is the more likely scenario.
Okay. Is there plans to do such spectroscopic follow-up?
Yeah, so right now, and what has been taking place is that we're collecting a lot of spectroscopic follow-up for the TESS stars that are being observed right now and has been observed. So those are undergoing studies, not necessarily by me, but by the team of astroseismologists in Leuven and our collaborators. So that's taking place right now. So we hope that soon we'll have some very exciting results available. The stars that I studied were from the Kepler mission. So for those that do have some spectroscopic follow-up already, that's been used in the astroseismic modeling, but I haven't used the abundances yet. So that's the next step, basically.
Okay.
For these studies.
Do you anticipate there being another paper on different sectors within the Kepler? So this was sectors 1 and 2. Will there be a similar study in other sectors?
Yeah, so for the TESS, so there already some studies out classifying stars. All OMB stars observed by TESS in 18 sectors. I know there's a paper out already, I think, on this. So that's both looking at OMB stars, but also ANF type stars.
Okay.
So they've gone through and made also an initial classification of the stars. So, you know, if you want to study a pulsating star, you have a starting point, basically, from where to start your analysis.
Cool. How about, are there any planned missions beyond TESS?
Yeah, so the next mission that will be important for us astroseismologists is the Plato mission. So I think exactly in which way they're observing or which field will be chosen is still under debate to my knowledge. But that's the next big space mission that's going to, in our sense, take over a bit from TESS afterwards with these.
Is there a planned observation? Is there a planned launch date for Plato, roughly? I mean,
I think it's in 2026.
Oh.
Yeah,
so
a few years.
Yes.
Yes.
Okay. Very cool. Very cool.
Yeah, in about 6 years.
Oh yeah, that's awesome. Good. So it seems like there's a bright future here in O and B star astroseismology.
Definitely.
So very
for
cool.
Sure.
For those of you who would like to get more and get your hands on perhaps May's thesis, now that she's Dr. Pedersen, you know how to contact her. We won't be putting her email address in a YouTube video or in the description down below, but feel free to reach out to her and contact her. And May, I want to thank you so much for taking some time today and chatting about your very cool paper.
Yeah, thank you for inviting me.
All right. Thank you, everyone. Bye-bye.